All right, so for lab 4, you want to log on to Canvas, click on the lab folder, and then go straight down to lab activity. So click on lens equation to find the activity, and the recording will be in this folder once it's been recorded. On the the lab data, you should download the lens equation, the Excel file, and work from there. Okay. All right. So let me bring up the file. So lens equation. Lens equation is equation to describe to find the image of that is formed by either a lens or mirror. So for lab 4, you'll be given, the first activity is that you're given a lens, a conversion lens, and you want to apply the lens equation to find the focal length of that lens. So the equation, so this is the one that involves involves two curvatures, but for thin lens, which is the one that you're going to use in the lab, is this equation. The 1 over I, which is the 1 over image distance, plus 1 over O. O is the object distance, and that's equal to 1 over F. Okay, so this diagram indicate how the image are formed, which you have learned in the lecture course. So we're going to utilize this equation to find the focal length. So how do we do that? Basically, we're just going to change the position of the object and find where the image are formed. So instead of just one set of data, one data point, you're going to build up several data points, and then you're going to plot. You're going to do plotting, to get the focal length. Okay, so that consists of first part. Now regarding so for conversion lens, it's very easy to find the focal length because you actually find the real image, and you can by applying this equation, then that becomes very straightforward. What about when you have a divergent lens? When you have a divergent lens, you can see that when you have an object that's placed in front of a divergent lens, then it's going to produce a virtual image. So it will be very difficult to, in principle, to find the focal length of a divergent lens. So what we can do is that instead of just finding that directly, we can do it indirectly. So in other words, we're going to use a two-lens system. One consists of divergent lens, one consists of a divergent lens and a convergent lens. And we're going to change so we have the original object distance, and we have the final image distance. And then we're going to change the object distance, and then in response, the final image distance will be different as well. And then from there, you can figure out what. And then assuming that you already got the focal length from the first part, then of course you will be able to deduce the focal length of the divergent lens. Okay, so that's basically the plan. So the two lenses you'll be dealing with are the one is convex lens or conversion lens, which has a focal length of 100 millimeters. So you want to change that to meters. To change that to centimeters. So that's 10 centimeters. And for concave lens, which is a divergent lens, so your focal length is negative 15 centimeters. Okay. So the setup is like this. So you have a light source, and you have a lens holder that has a lens, and then you're going to place them like this. So you have the light source, which is located at the what we call the X objective objects. So this is the O, and this is the locations of the conversion lens. So we use XCOM to indicate that's a position for the conversion lens. And so this is the screen. So at screen, so XCN indicate the position of the screen. And so you're going to change, instead of changing the light source, we're just going to fix the light source at its location, which is located at 0. And we're just going to change the locations of XCOM. so that the difference between the x-com and objective is going to give you the it's going to give you this, the object distance. And then you're going to move your screen until you see a focus shot image formed on the screen. So the image distance would just be xcn minus xcom, just based on this diagram. It's very easy to see. So then once you have the object distance, once you have the image distance, and then you're going to plot. So if you go scroll down to the analysis, you are going to plot. Let me just do this. So you can see that for the first part, this is how you calculate O, object distance, and this is how you calculate image distance. Just follow that, you won't get wrong. And once you have that, and then you want to plot 1 over O versus 1 over I. Okay, so you can see that 1 over O is in the y-axis, 1 over I is in the x-axis. So once you do that, if you remember, this is 1 over I plus 1 over O, that's equal to 1 over F, right? So when you plot 1 over O versus 1 over I, then of course the intercept. The intercept is going to give you the inverse of the intercept is going to give you the focal length. So from there you can figure out what the focal length is. Okay, so that's basically what you want to do for first part. And for the second part is that we're going to have two lenses together. So these are the two lens system. Okay, and so this is the object. This is where the light source is. Indicate XOBJ. We don't change anything here. And then this is the diverging lens, and this is converging lens, and this is the screen. So when you do this, what we're going to do is that the XDVI indicate the position of diversion, XCON indicate the position of converging lens, XCM indicate the locations of the screen, and the D here is the separation between these two lenses, which is a constant. D is a constant. We don't change that. So just based on this diagram, it's very easy to deduce that the object distance, which is XDVI, this one, minus XOBJ, okay? And the image distance, so this we call that O1, okay? This is like, the position in front of the first lens. And then we don't get the I1, we don't get the O2, but we do get I2, the final image distance. So the final image distance is this, X screen minus X com. Okay, just based on this diagram, it's very easy to read, to deduce. So make sure that you just use this equation to find out O1 and I2 in the Excel file. So you might wonder, so how do we get the I1 and O2? What you need to do is that you want to utilize the lens equation, and then based on this diagram to deduce that. So the following steps tells you how to do that. Let me scroll down a little bit. Okay, so just based on this diagram, you can see that so we have O1, we have I2. So now we're going to, and this is your second lens, which is a conversion lens. So we're going to use that 10 centimeters. Okay, so F2 is 10 centimeters, and then we want to find out, because we know this F2, we know the I2, so we can actually use lens equation to calculate O2. Okay, so your O2 is actually the inverse of 1 over F2 minus 1 over I2, right? Just by straightforward, just applying the lens equation, very straightforward, because F2 is is given, I2 is you already calculated that, so you can calculate O2. Once you calculate your O2, knowing that your O2 is the image produced by the first lens, right? The image produced by the first lens is the object for the second lens. So you can actually infer your I1. And your I1, because so you have your O2, where should your O2 be? your O2, which is the which is an image produced by the divergent lens, it has to be in front of a divergent lens. Okay, so your O2, your O2 has to be so your I1 or O or I1 has to be somewhere in front of the lens, and we know the separation here, so you can actually use this equation that your I1 is D minus O2. And what you might wonder, why isn't why didn't we use O2 minus C? And that is because your I1 is actually a virtual image, and so it has to be negative. So that's why you use D minus O2. Okay, so you apply this equation to calculate O2, and then use this equation to calculate I1, and you have your O1 already, and then you calculate your I1. So you can so you have the I1, 1 over I1, you have the 1 over O1, so you can actually calculate. You can calculate the focal length for f1. Okay, so you're going to apply the length equations again, and so here you basically you would do the same thing. You will plot. You will plot 1 over O versus 1 over I, and the intercept is going to give the inverse of the intercept is going to give you the focal length. Okay, so let me see where there should be an indication that what the D is. Okay, so the D, let's see, the D should be okay, place conversion to right and the required separation. So your D here is 5 centimeters. It does not change. Okay, so that's basically the overall how you would do this experiment. You're given the known, and based on the known, you calculate the unknown, and then the unknown becomes known, and then you plot the two known quantities to infer the focal length of the two for the two lenses. So the data point, the data points will be given to you, so you don't have to enter the data points to this table. Okay. So what I'm going to do is I'm going to bring up the data. So that will be an Excel file. You should download that. You should download that Excel file and use that Excel file to work. So I already organized the table like this. So utilize this table. So in other words, you have the XCOM, that's all given, and you have the location of the screen, that's also given. The locations of light source is 0. And then so your O, so what is your O? You can just follow the steps. That basically will be the S column minus X object. And then once you have your O, you can create a column to calculate 1 over O. Okay. And then I is the S screen minus S column. So the difference between these two gives you I, and you can calculate 1 over I, and then you can plot the 1 over O versus 1 over I. Okay. And now for the two lens system, the data are also given. So you have the O1. So if you remember, O1 is calculated using XDIV minus X object. Basically, it's the same as that one. And then calculate 1 over O1. And your I2 will be the S screen minus S com. Okay. Okay. So the difference between these two gives you I2. And then your O2 is use the lens equation. That will be the inverse of the 1 over 10 minus 1 over this column, 1 over I2. And then your I1 is D is 5, and then minus O2, and then after you calculate your I1, calculate the 1 over I1, then and then you plot the 1 over O1 versus 1 over I1 in order to get your focal length. Okay, and then you're going to compare to the actual value. For conversion lens, the actual value is 10 centimeters, and for divergent lens, the actual value is negative 15. And then I can calculate the percent error, for each lens. Okay, so that's basically what you want to do.